Hey guys, in this video we will be going over two interview problems, specifically dealing with cyclicity. The first interview problem will be discussing how to return a true statement if a cycle exists. And in the second interview problem, we'll take it a notch further and return the first node of a cycle if it exists. And these are two LeetCode problems that you can check out yourself. I put them in the description below, and you can work on them yourself. But I'd like to take the time in this video to discuss each problem so that you understand the concepts behind it. So here I have a linked list, and in this linked list we have the head node and two iterator variables, runner and walker. Now, runner and walker kind of speak for themselves in terms of what they do, where runner and walker are iterator variables, and the runner variable goes two linked nodes every time it's run, whereas the walker variable is run every linked list node. So the problem we have to figure out here is whether this linked list in particular has a cycle in it. And off the bat, I don't even have to put the values in the first blocks of each node. You can see that there's no cycles because there's no node that goes to a node before, like so. If there was this purple arrow, then yes, this would be a linked list with a cycle where the tail node actually cycles to the node before it. Another example is here where the linked list goes to any of these nodes in a cycle formation. So the question that we have to figure out is how to implement code that will return true when a cycle exists. And there's one way to do this, and it's not obvious at all off the bat, but it's a mathematical formula. It's called the Floyd's algorithm, where we say that if we have runner going every two nodes and walker going every one node, if a cycle exists, then runner and walker will meet each other at some point. So let's create a loop here, and let's run a sample iteration with runner and walker. So runner is going to be here in the first iteration of the runner variable, whereas walker will be here in the first iteration. Now, in the second iteration, runner is going to be skipping this node and going to this node. So runner will be here in the second iteration, and walker will be where runner originally was. Note that these two are not in the same place right now because runner is actually here at time 2 while walker is still here at time 2. Just because runner and walker are in the same node doesn't mean they're at the same place, because they're not at the same place at the same time. So once runner and walker are on the same node and these numbers match is when we can stop iterating and prove that runner and walker will eventually meet. So now that we have runner at 2 and walker 2 in their positions, runner 2 is going to skip a block and then go to the next block. And as you can see, we have a cycle here, which means that it's going to skip this node and it's going to go right back to this node again. So we have runner 3, and then we have walker 3. Finally, runner 4 is going to skip this node and go right back here. So runner 4, and finally walker 4. And we finally found a match where runner and walker are in the same node at the same time. So now that we've proved cyclicity, by showing that runner and walker are at the same place at the same time. Let's try doing this if, say, the cycle was a little bit bigger. So let me copy this and do the same thing, except the cycle is going to be 3 nodes long. So the same setup, and let's do the whole thing again. I'll be a little bit more quicker this time. So runner here, walker here, runner here, walker here. Runner is going to skip this node and go to this node. So runner is here, walker is here. And we've finished showing that runner and walker have showed up on the same node, and because of that we can prove that this linked list has a cycle. So these are 2 examples, but just trust this theorem that if you have 2 iterator variables that go at different speeds, specifically 1 node and 2 nodes with each iteration, then if they arrive at the same node eventually, then the linked list 100% of the time has a cycle. So with this theorem in mind, we can finally start implementing our cycle definition that works on returning a true statement if a cycle exists. So let's call it def cycle, and we'll have 1 parameter, head. And this is the linked list that we're going to be testing for cyclicity for. And as you can see in our example, let me actually copy and paste this. We can see that head and runner and walker are all starting at the same node. So we can say runner equals walker equals head. Okay, now we have to do this walker and runner iteration where runner goes 2 nodes every time it's run and walker goes 1 node every time it's run. In order to do this, you have to do walker equals walker.next and runner equals runner.next. Runner will have 2 .next variables because runner is going twice. And these .next attributes are defined in a node class, like so, where class node has an init function definition, where value equals none, and we have 2 attributes, self.value, which equals value, and self.next equals none. So this is going to be before this function definition, so that's where the .next is coming from. Let me minimize this. Okay, so now that we have the iterator variables declared, we have to put an if statement that deals with the condition where runner and walker are at the same node, at the same place at the same time. So we have to do it like so. If walker is equal to runner, return true. Or else, if walker and runner never hit the same node, we return false. Now, you might think we're done with this cycle statement, but we have to deal with the edge case where the linked list has no cycle. So say that we have a linked list, and let me copy and paste this. Do it right here. So we have a linked list that does not have the cycle, and it's just a straight linked list with no cycle. If we iterate this like we have in the earlier example, we have runner here, then runner here in the second iteration, and then walker is here in the first iteration, second iteration, third iteration, fourth iteration. Now, how do we move runner here if it's null? Well, we can't, because the next node after null is nothing. We can't do that. So we have to have some sort of while loop that prevents this from happening and makes sure that we iterate walker and runner only if there's an existing node that can be iterated through. So one way we could probably do this is say while runner, because whenever runner is here, the node exists. So we can say while runner do this iteration. But what if we have an even number of nodes, like so? Where runner is here, but runner has to go past this node to this node, and this is null. So we have to have another while check that says while runner and runner dot next, where we have to check for not just runner, but if runner.next exists as well. So runner.next exists here, so we can iterate it. And then the next time we go to this while loop, we have to move runner to null, but runner.next is nothing. So therefore, this while loop no longer holds true. So we have to have both runner and runner.next to account for a linked list that has an even number of nodes, and then a linked list that has an odd number. Or sorry, reverse that. A linked list that has an odd number of nodes, 1, 2, 3, 4, 5. And then runner.next is for the condition where a linked list has an even number of nodes. So let's write that while statement up here. While runner and runner dot next, we do everything here. And then finally we return false. Now I'm going to link the LeetCode interview problem where you can actually write this into the LeetCode submission area, and we'll get the right answer. And definitely check that out and try to do this problem yourself with your own implementation, and just be able to understand the concepts that I've discussed. And if you do decide to use my implementation, understand how it's done rather than what I wrote specifically. So that's the first interview question. And now the second interview question is, if we have walker equal to runner, instead of returning true, we need to return the first node of that cycle. So say we have a cycle here, and we identify walker and runner as equal, so therefore this linked list has a cycle, we have to return the first node or the head node of the cycle. So in other words, we have to return this node. If we have a cycle that has 3 nodes, we return this node. So this is actually kind of tricky if you don't really know how to deal with returning a third node. And in order to do this, we have to introduce a third variable. And let me erase this. So the good news is that we can actually use the same stuff that we've been using in our original implementation, and we can add a few lines of code to return the first node or the head node of the cycle. So in order to do this, we have to erase this stuff, and we have to introduce a third variable. Specifically, we'll call it seeker, that basically iterates through the linked list while this cycle is going on and meets the walker variable at the head of the linked list at the same time and place. And this can be mathematically proven, and I won't be doing this in this video, but please feel free to let me know if you're interested in understanding the mathematical formula. But if we introduce a third variable, the moment when runner and walker are equal to each other, then as we iterate this again, we will have seeker and runner and walker at the same place at the same time. So let's actually do that iteration. So here we have runner and walker at time 3, and at time 4 walker will be here, and at time 4 runner will be here, since runner 3 is here and we're skipping this node to get to this node. And then finally we have to remember that seeker is here at seeker time 4, because at time 3 seeker is introduced to the head node, and then at time 5 runner will be right here, while walker is now here and seeker is now here. So magically, and this is actually really cool to me when I first learned about this, seeker and walker have shown up at the same node at the same time only when we've introduced the seeker variable, the moment when runner and walker are at the same place at the same time at the same node. And we can prove this with a cycle that has 2 nodes, where runner, so this is the second iteration, third iteration, walker is here at the, let's see, nope, didn't do that right. Runner is here at the first iteration, runner's here at the second iteration, walker here at the first iteration, walker here at the second iteration, walker's here at the third, and then runner is here forever, while walker is here at the third iteration. So at the third iteration, we introduce this new variable, which is seeker, and we'll call it at time 3. And then at time 4, seeker is here. Let me make this a different color. seeker is here, and at time 4, walker is here, and runner is here. And then at time 5, seeker is here, walker is here, runner is still here, and finally at time 6, seeker is here, walker is here, and runner is still here. So boom, we've proved that seeker and walker will always show up at the same node, assuming that seeker is introduced to the head node at the same time when walker and runner are at the same node. So now that we've proven that, we can finally go on to our implementation to return this node when seeker reaches that node. So if walker is equal to runner, seeker is equal to head, right? As we've shown here, where the moment runner and walker are in the same node at the same time, we introduce a seeker with a time of 3. So seeker is equal to head. And what's the next step? Well, we have to create a second while loop. While seeker is not equal to walker. This is an exclamation point. While seeker is not equal to walker, we make seeker increment to seeker dot next, and we make walker increment to walker dot next. So this is basically the same thing we've been doing with the seeker example, where seeker is not equal to walker at time 3. Here, seeker is not equal to walker at time 4, because this walker is only at time 1 and it's not the same time that they are both existing. Seeker, when it iterates to this node, is finally at the same place as walker is, at the same time as well, because it's time 5. So this while loop will increment the seeker variable and increment the walker variable until seeker is equal to walker. And when seeker is equal to walker, we will return walker, because walker is now where seeker is. And that's pretty much all you have to do to show that walker exists. And the final step is to return null if this statement is not true, or in other words, if there's no cycle, like so. Return null. And that's pretty much it. We have 2 function definitions for 2 different but very similar interview questions, where in the first case we're returning true if there's a cycle, and in the second case we are returning the head node of the cycle if a cycle exists. And these are 2 different linked list LeetCode problems that I will be posting in the description so that you can work on them yourself. Thank you so much for tuning in, and if you have any questions, feel free to let me know. I'd be glad to help. Want to inspire other people to continue their journey into data structures and becoming the best programmers they can. Thank you so much for watching, and stay tuned for the next video. Peace.